Hello everyone, welcome back to today's lecture number 12, where we're going to talk about the numerical results of the three different applications. We'll talk revisiting them again and the conclusion of our model. So first, let's revisit the application number one. We're going to see that we got 183 countries, four different policies in a UN setting. We got those four different topics. We set our prerequisites and we design our models using those rules that we discussed in the previous lecture. As for the experiment designed, we got several different parameter settings to a total of 48 different configuration possibilities, as well as two distinction, whether using social welfare and the national equilibrium constraints. As for the evaluation, we use the goodness of fit on those three countries, and meaning that the prerequisites fixed by construction are excluded from accuracy measurement. And also, we can only measure the accuracy on this feature number 1 to 3. The four features of like Palestine and Israel recognition is fully prerequisite fixed, thus we cannot manage to analyze that. So let's look at the result here. The result comes from the best performing instance where we got kappa equals 0.9, rho equals 0.1, and density equals the 80% network. For LGBT rights, we got 70 to 80%. For CO2 and immigrations, they are almost at 70 to 80% as well. And we also, by looking at the column between social welfare and the national equilibrium, we see that with those national equilibrium constraints, it consistently outperforms social welfare on these three features. And we also prove that all analyzed national equilibrium solutions are also social welfare solutions. In a sense, the national equilibrium constraints is a refinement of the social welfare solution. It's not actually an independent solution concept. So why does national equilibrium win in this case? The reason is about the strategic consistency. In fact, social welfare maximizes total agreement, but it can include country stances that are not individually rational, given that the country's neighbors. But national equilibrium add that refinement, and it just proves that countries behave strategically to its own benefits, not in a collective way, but only try to maximize what itself without taking account of the choices of the others. What did I say? Without taking into account the utility of others, only the one of itself. So let's look at in terms of the CPU solve times in the first applications. For social welfare solutions, it can range from under 3 seconds to over 400 seconds. But for national equilibrium, it's almost twice as fast. And why is that? One may think that national equilibrium has more constraints, but also more variables. It's not immediately obvious that why it is performing faster in this case. But we know that it's not it's not slower because the linear programming relaxations of the both formulations are matching to each other, are coinciding. So the integer gap between those models are small, and Cplex, our solver, finds tight bounds without deep branching in the sense. And to the right-hand side, we also see that we observe what we call a network density effect. In fact, the 80th percentile, should say, density is outperforming the 90 percentile network. It proves that better connected graphs, meaning that we got fewer singletons, fewer countries having no links to others. And in this case, it can be having a better accuracy than a 90 percentile where you got more singletons. In the same way, the trinomial rule is also performing better. Now let's look at the second application about the missing data application, missing data imputation. As before, we compare our voting game model with the best KNN baseline. So KNN has a K that can range from 3 all the ways to 15, and we pick the best out of them. And we see that our voting game models outperform KNN in 6 of the 8 data sets that we have in here. And why it is the case? Um, Social welfare solution, so the voting game, which is the social welfare solution, so we show wins for two different reasons working together. So first is that the endogenous threshold I can be adapting for each individual. So meaning that each point gets its own effective K rather than having a common K for every individual. The second reason is that the joint imputation implies all missing points in the data set can be imputed, can be solved immediately in a simultaneous way. Instead of looking individuals per individual and having no link to each other, they are solving in a simultaneous way. And this can especially benefit when the missing data tend to be can be clustered to each other. This is consistent with how we design the points of the missing data generation method. Um, so these are things that our voting game models achieve, but the standard KNN model cannot do it. So that's why we think this is outperforming. The other aspect is about the Nash equilibrium constraints. In this second applications, the Nash equilibrium does not perform particularly well, but this is explainable by a conceptual reason. Features in a imputation task are data, not real strategic interaction between the data. So there's no agent deciding to consume things that are um, sorry.